Okay, good morning. So, in the last class, that is in lecture 2, we had started on discussion of static and dynamic characteristics of an instrument. And we had explored various static characteristics like accuracy, precision, range, resolution, etc. Okay, and so in this lecture, we'll be concentrating more into the dynamic characteristics and how various dynamic characteristics, how can they be used to ascertain the quality of performance of an instrument in practice. Okay, so as we have seen that in most cases, an instrument does not instantaneously respond to the input quantity because of some internal dynamics that are present. A classical example is of a thermometer. So, all of us have experienced that if you want to take the temperature of your body using a thermometer, as soon as you keep the thermometer on your mouth in your mouth, you're not getting a reading. You have to wait for some time for the reading to settle to certain value. So that it is clear that the response or the actual reading doesn't come out instantaneously. Okay, and that is due to some internal dynamics of the instrument, of the thermometer in this case. Okay. Now, we have seen in the last class the mathematical model that describes the relationship between the measured quantity and the reading, the measurement. Okay, so in this case, so Qi is the input quantity that is to be measured, and Qo is the indicating signal or the reading of the instrument. In case of the thermometer, this is the reading of the thermometer, and this is the actual temperature that the thermometer is being exposed to. Okay, and typically in every instrument, the input quantity powers the instrument partially, so it gives an auxiliary power to the instrument in case of a active transducer, in case of an active instrument like in a case of multimeter, and it it completely powers the instrument in case of a thermometer like a mercury thermometer. Okay, where the complete energy for the instrument, for the response of the instrument, comes from the measured quantity. Okay, in any case, the power that is delivered by the measured quantity drives the instrument and changes the indicating value, indicating variable, and that is it causes a, in more simpler word, it causes a reading. Okay, and the manner in which the instrument responds depends upon how the input force or the energy that is in the sensed variable, how it affects the indicated variable, and this effect may happen in three different levels. So you can, I'm using the terminology of a level, but yeah, let's get into that. So this effect may be an instantaneous effect, like the relationship between the voltage and the current across the resistor. Okay, so as the voltage across the resistance changes, the current through the resistor also changes instantaneously. Okay, so that is one level. Okay, or else it can affect the rate of change of the indicating variable, like heat to temperature. So if I am applying heat to an object, the temperature of the object doesn't change instantaneously, only the heat being applied, the heat being applied is proportional to the rate of change of temperature of the object. Okay, so either it affects the object or the variable itself, okay, something like x, and or else it affects the time derivative of the variable, the rate of change of the variable, or in a third case, it can affect the second derivative of the variable. That is like a force to position relationship. Okay, a force is applied to a mass, so it affects the acceleration of the mass, that is the second derivative of the position of the mass. So these three levels of cause and effect relationship can be present. Okay, so it is very trivial to and when the rate of change is not when so when the change of the input variable directly affects the reading or the output variable, such an instrument is called as a zero order instrument. Okay, it's like the output of a potentiometer responding to a change in the input voltage. So the input voltage, when the input voltage changes, the output voltage is just directly proportional to the input voltage. So you would have a input to output relationship that looks like this, and there is no d by dt sort of terms in this. So it's a zero order instrument. There is no dynamics at all in the instrument. And in this case, the response is instantaneous and the output follows the input shape faithfully. That is, it's a high fidelity instrument. Okay, so if you see the step response, so as the input, there is an input step change in the input, the output also changes like a step. And if you see the frequency response of a zero order instrument, what you would find is that there is a constant gain at all frequencies, and the phase difference between the input and output is zero at all frequencies. Okay, and this actually implies that a zero order instrument has inherently high fidelity and a frequency independent behavior. Okay, now let's go to the first order instrument. So in case of a first order instrument, the measured quantity affects the first time derivative of the instrument's output. Okay, so that, and as I said earlier, the classical example of such an instrument is a thermometer that is kept in a bath of a liquid in some particular temperature. So the relationship between the reading of the thermometer QO and the input, okay, is given by a first order differential equation in this case. And now there can be two sets of situations. One is when the constant associated with Q0 is equal to 0, or the constant associated is greater than 0. Note that we are not considering A0 is less than 0 case, because that will cause that will lead to a situation where for a finite value of input, the output just increases exponentially, and that is an impractical scenario. You don't, so which would mean that from a finite input, infinite output is being generated. This is an impractical scenario that doesn't happen. So this A0 less than 0 situation is not being considered at all. Only two situations where A0 equal to 0 and A0 greater than 0 are being considered. Okay, so let's look at these two situations. Okay, when A0 equal to 0, what you have here is that this term disappears and you only have an integrator, and so the output, the reading is just an integral of the input. Okay, however, and this seems true. This seems true in a situation because the rate of change of temperature is proportional to the amount of heat that is being present, that is being input into the thermometer. Okay. However, there is one thing: the thermometer also, the rate at which the thermometer is able to uh, heat up is also proportional to the temperature difference. That is, T, say if the thermometer's temperature is the TF and the input temperature is TI, the rate at which, so d by dt of TF, the rate at which the thermometer heats up, is actually proportional to the difference between these two temperatures, or rather it should be Ti minus TF. Okay, so then the proportionality will be a positive constant. Okay, so let me write it in that manner. Okay, so so basically what you have here is that in the ideal situation you will have an equation like this, but again, if Qi is kept as a constant, that is, if this temperature of this bath is kept constant, the expectation would be the thermometer's reading will increase to an extent and stop. So the thermometer is not actually a pure integrator also. It's very close to a pure integrator, but it's not really a pure integrator. This sort of an equation where the rate of change of the temperature of the thermometer being proportional to the temperature difference is more practical. Okay, and this sort of a response is called as a first order response. Probably you might have seen this sort of, you may study such a response in your basic control course. Okay, so you basically have a first order response in a few instruments like the thermometer. Okay, now assuming such a first order system, first order instrument is connected suddenly to an input quantity. Okay, then what would happen? So if the input quantity is a constant and with a constant c, then the output quantity for the type of relationship that was described in the earlier slide, the output quantity will be described by this time function. Okay, and if you draw, you would get an equation, you would get a graph that looks like this. So the measured quantity is a step signal because there is a sudden connection. However, the instrument responds along this line. Okay, so it is clear that by the time, so you have to wait for some time for the instrument to respond, or to give an indication, to give a reading that closely matches the actual measured quantity. Okay, and typically this response time is quantified by this time constant. Now what is the time constant? Time constant is the time taken for the reading to reach the actual value if the initial rate of change, that is the rate of change, the slope, the initial slope, if it is maintained, the time taken to reach this measured quantity, that is called as the time constant. And usually a first order instrument is characterized by its time constant. The greater the time constant, the more sluggish the instrument. Okay, so as I said earlier, in this case the time constant is a0 by a1. Sorry, the time constant is not a0 by 1, it should be a1 by a0 in this case. Okay, and this time constant would cause a lag in the reading. Okay, so it causes time lag before the reading can actually be taken. Okay, now let's get into second order instrument. A second order instrument, as we had seen earlier, is an instrument where the input affects the second derivative. Okay, that is like a force to position relationship. Okay, so in this, the instrument indicator mechanism has a mass or inertia, and its position is being changed by application of a force. Okay, as in the case with the first order system, let's start with the simplest case, where you have a force that is applied and that changes the second derivative of the position. Okay, now again, the first quantity is that now if you have a force, if a force is applied, Fi is applied to a mass, then you will have some acceleration E, and now again it is impractical that it keeps on accelerating. Okay, and if it keeps on accelerating, reading cannot be taken anyway. So what you would need is something called as a control force or a restoring force. That is a mechanism by which you keep the indicating signal at check, and you store the force, you store the energy that is delivered by this force in the form of potential energy. Now in a mechanical system, this potential energy, this mechanism for storing potential energy can be a spring. In an electrical system, it would be a capacitor. Okay, the spring stores position based energy like a potential energy. Okay, and the capacitor stores charge, that is again a form of potential energy. Okay, now since you have a restoring force, you would have this additional term that indicates the energy storing element. However, the next problem comes that now if you have this sort of a system where you only have the input force and a storage element that stores potential energy, the output to input relationship would look like this. Okay, for a constant input, the output to input relationship would look like this. And for a step change, so you give a step change in input, and the output is an oscillatory signal. It keeps on oscillating, and what we are interested in is getting a reading. So if you have an instrument that keeps on, whose, let us say it's an indicating instrument, so you have a pointer that keeps on oscillating, then it's of no use. The reading should settle at some value, so you need something to damp the reading. The sustained oscillation is of no use, so you need something to slow down or dampening the indicating mechanism so a fixed reading can be obtained. Okay, and this damping is usually provided by friction in mechanical system or eddy current in the electrical equivalent. So you can have a friction based damping, or you can have an eddy current based damping. Okay, in both cases, the important point is that damping is provided. Okay, let's move ahead. Now if you add this damping coefficient, okay, this damping is sort of slowing down whenever there is velocity, it is slowing down the velocity so that the reading comes to a constant. So the damping is proportional to the velocity or the time derivative of charge, that is current. Velocity being the time derivative of position, current being the time derivative of start. It is basically, the damping is proportional to some velocity equivalent. So as a whole, you get this second order differential equation that is relating the input quantity that is to be measured, and the indicated value of the instrument. Okay, now let's go ahead and see that what would happen in this case. Okay, so we have this second order differential equation, and to simplify things and to get in a standard notation, let us define omega n, that is called as the natural frequency, that we will say is the natural frequency, and zeta, that is called as the damping ratio, okay, as these two quantities. Okay, now what would happen is that now if I use this, then this equation can be rewritten in this form in terms of zeta and omega n. Okay, now if you look at the characteristic equation, that is the roots of this equation equal to 0, that is if you say d square plus 2 zeta omega n d plus omega n square equal to 0. If I take this characteristic equation and try to determine the roots of the characteristic equation, we end up two roots being positioned at these two locations. Now, depending upon the value of zeta, I can either have real roots, repeated real roots, or complex roots. Okay, so if zeta equal to 0, then what you have here is this goes off. You have two roots on the imaginary axis. Okay, so you have omega n or j omega, or actually it will be plus minus j omega n. Okay, so you have two roots on the imaginary axis. There are sustained oscillations, and this prospect is now you already considered, you already seen that that is not really a useful one. And anyway, if zeta equal to 0, it would mean that this term was not there, but we do have the damping now, which would mean that we are not going to see this part now. Okay, let's go to the next ones. Okay, so the next one is when zeta is let's go to the overdamp. So when zeta is greater than 1, then you have two distinct real roots. Okay, when zeta is equal to 1, then this part goes off, so you have two repeated real root. Okay, and when zeta is between 0 and 1, then you have complex roots. Okay, so when zeta is between 0 and you have complex roots, you have oscillations. However, since there is also a real part, it's not only imaginary, there are also real parts, so you have oscillation and you have some sort of damping. In these two cases, there is no oscillation. Okay, there is damping, but the quality of damping would depend upon the interaction between omega n and zeta. Okay, let's look at those cases now. Okay, now let's see the responses. When zeta is between 0 and 1, that is when the system is underdamped, you get, as I said earlier, you get an oscillation and also damping factor that is present. Okay, where this omega d, which is called as a damped natural frequency, is written in this manner. Okay, when zeta equal to 1, you have a response that has no oscillation, there is a damping, and the damping factor, okay, is also enhanced by this omega nt term. Okay, and when zeta is greater than y, you have two distinct roots. Okay, and the response can be succulently written in this manner. So in the case you have this as the summation of two sinusoidal terms, two exponential terms, not sinusoidal terms. Okay, something in this manner. Okay, and if you try to plot it, typically you get responses like this. Now in this case, in a ramp-damped case, you see that there are sustained oscillation, and these oscillations don't die out. This is a useless one in that case. Okay, And if you go to the other extreme, the response E, you see that this is really, really sluggish. In fact, if you look at the point at which these responses reach the final value, the actually the settled value for the first time, you see that as damping ratio increases, the response becomes more and more sluggish. However, you also see that there is less oscillation as the damping ratio increases. So there is sluggishness, which is a negative quantity, but also less oscillation, which is a positive sign. Okay, so this itself will see that you have to be really careful in the choice of damping ratio for your instrument if damping ratio is a choice. So if you can vary damping ratio, okay, then there would be some middle ground that has to be found. Okay, as we have seen that in this case, as the value of zeta increases, the speed decreases. It becomes more and more sluggish. Okay, and as zeta increases, the oscillation also decrease, which is again a positive sign. This is something negative. This is something positive as zeta increases. Okay, and as zeta increases, if you see the response time, okay, the response time, that is the time after which the signal or the output signal stays within some plus minus alpha error, okay, from final value. Okay, so if you draw a small bound around this final value, and if you see the time after which it stays within this final value, you of course you would see that as the damping ratio initially, as the damping ratio increases, since the response becomes more tight, the oscillation, it gets damped more, it would the response time will decrease initially. So if you plot uh, uh, zeta versus response time, okay, ts, initially it will decrease. Then as the damping ratio is increases, as zeta goes greater than 1, the response itself is taking a lot of time to even reach into this bound for the first time. Okay, the response time then starts to increase. So the sweet spot where the response time is minimum is what we want to catch. Okay, and this ideal choice at the where the value of damping where the response is quickest is the critical damping. However, this is zeta equal to 1 and we are dealing in a practical instrument, okay, where it is very, very difficult to tune the instrument in a manner such that some parameters is equal to something. Okay, even if you say, even if you go to a lab and you want to pick a resistance of say 120 ohm, you can never assure that the resistance is exactly 120 ohm. It will be 120 plus or minus some percentage. Okay, this error is always there. Okay, so even if you try to go for a critical damping, you may never get a critical damping. Okay, in fact, you most probably will not get a critical damping. You will not be able to achieve critical damping exactly. So in which direction should you err? That's the next question to be answered. It is undesirable to have greater than 1, zeta greater than 1, that because the response will become more sluggish. Okay, there are no oscillations, but there is no advantage also. Okay, the response anyway did not have any oscillation when zeta was equal to 1. So, and it doesn't have any oscillation when zeta is greater than 1. However, the response has become more sluggish. So you don't want this. It's undesirable to have zeta greater than 1. And you have to, and zeta being much less than 1 does give a speed, but it increases oscillations, and that is also not good. it will not, the response time is not, that it's not achieved at all, the response time advantage is not there at all. So you have to, so the suggestion is that you get zeta to be between 1 by root 2 and 1. Okay, somewhere in this range you have zeta. So now instead of fixing zeta equal to 1, you can go between this range and choose your instrument or design the instrument in a manner such that the damping ratio comes to this value, falls in this range. Now exactly why this 1 by root 2 is being chosen, that is something that I would leave for you to explore. Okay, so whatever was covered in today's lecture, okay, that can be seen in chapter 2 section 4 of the book on measurement and instrumentation. Okay, and with that we come to the end of this lecture. Thank you for your time.